Okay, thank you for sticking around for the bitter end. Hopefully I can make it short and sweet. I'm a Willis Research Fellow at Bristol University, and I'm going to explain or talk about a new project where we're comparing the outputs from global flood models to see what we can learn. So a little bit of background. As we've heard, GFMs are now a practical reality, and there are a lot of models excuse me, and lots of interest in the development and the use of these models. So this is where this project came from. The Global Flood Partnership met in March this year, and I identified this as a research priority. And Willis Research Network has kindly agreed for me to spend my time doing this comparison project. So at the moment we've got three models, or results from three models, GLOFRIS, Matsira and Karma flood, and then ECMWF and Karma flood. So I'll explain a little bit about those in a minute. So methodology, we're looking at the spatial extent in terms of the African continent. This was the location or area, if you like, that most modelers seem happy to share their results for, and also there was a huge amount of interest from the development community in terms of that area. We've got flood output from hazard data, this is, not event data, for various return periods. So we've got that data from these three models. And we've analysed that for the continent, and we're also looking at the catchments and the country scale. We've also done an analysis of an SRTM MODIS water mask from Yamazaki of normally wet areas, just so we've got an idea of what we're comparing to. I must point out the aim here is not to find the best model, because there is no good model. It's really to compare and contrast and see what we can learn from these different model approaches. So it's a sort of collaborative approach, if you like. The project is ongoing and evolving, so this is just the first results as we go along. So the three models that I've got data for so far have a fairly similar structure. Some of the other models that have been promised are very different to this, but for the three that I've got, this is typically how they're arranged. You've got a climate data set that forces a land surface model, and that produces flows, and that's fed into a river network, and then a floodplain, and then that's downscaled into an actual flood extent and depth map. So all three of them follow something very similar to that. Here's a very quick overview. I'm not going to go into detail on all of these, but to show you actually a cascade of lots of different model choices, if you like, and data sets. Each has different climate forcing, different land surface model, and different river routing and downscaling and so on. But the key thing to see here is that essentially we've got similar scale output. We've got between 500 meters and 1 kilometer scale output, just to give you an idea of what we're actually working with here, which is quite impressive. So this is what it looks like for all of Africa. What do we get when we say, okay, let's add up all the area that's flooded for each of the models and each of the return periods? And this plot shows the results of that exercise with flood area by percentage relative to the total land area and return period along the bottom there. And you can see the various models displayed. There's GLOFRIS on the bottom, and then the Karma flood there, and then there's three models here from the ECMWF group. And the difference between these, I didn't mention that earlier, is that they each have a slightly different routing within the model. So everything else is the same, but one is a kinematic, one is an inertial, and one is an inertial with a different coefficient. So you can see they're clustered together. You notice they're quite different in terms of results, although they follow a similar pattern of, as you'd expect, increasing, you'd hope, increasing flood area with return period. So let's have a closer look at what that actually looks like spatially. So to give you an idea, this is the Niger River clipped to the Nigeria boundary. So rather than look at the whole continent, we just look at a main reach of a river that is fairly well understood and should be fairly well represented within these global models, and have a closer look at that flooding. And if we zoom in a little bit here, you can see that some of the models have small channels that aren't in other models, and that explains some of the difference you see in terms of area. But interestingly, the slide before with the graph on, it looks like there's no overlap between the models. There is actually a spatial overlap. It's just the total area is different. And you can see that difference here. You've got all of the results overlap in terms of the main channel, although you still get the same pattern in terms of total flooded area, with glow frizz on the bottom, the smallest area, and then ECMWF's model with the greatest area. And this is the output for that area, and you can see we get almost the same pattern. Interestingly, there's a bigger difference now between the three routing methods used by ECMWF, and that could well be because of the storage upstream in the Niger Delta, which obviously has a big impact in terms of the flows downstream. So moving on, we had some talk earlier about deltas around the world, and here's the results for the Nile Delta. I thought this would be interesting to show some of the differences you get between the models. Some of the models flow straight down the main channel to the coast, and then some of them spread out a lot. Now, it's important to mention here, I think Yamazaki did a nice talk earlier talking about bifurcation of deltas, and that's exactly what's going to happen here, is that models are going to incorporate these processes and improve their definition. So we've still got a bit of a way to go in terms of modeling some of the processes in some of the areas, but that's part of this exercise, is to look at that. So if we look at all the catchments for all of Africa, we plot them all on the same color scale. So you get glow frizz on the left here, over to ECMWF on the right. This is for a 100-year return period. And you can see that you get the similar scale in terms of which one's driest and which one's wettest. But there is a considerable difference in terms of spatial pattern. ECMWF shows a lot wetter West Africa, and also there are lots of dry catchments here in both these two models, but not so much in the ECMWF one there. And if you look closely, some of the catchments here, for example, are actually reversed in terms of which one's wettest and which one's driest. So not necessarily going to hold every catchment scale. So there's some interesting digging I've got to do there. So if we plot that up as a scatter plot of all the catchments, so same percentage flooded area, and then by catchment area, total catchment area, you get all the big catchments here with the Congo, the Nile, Niger, etc. And then a scattering of smaller catchments down here. You can see the dry catchments is zero flooding in these two models. Interestingly, we've got an increasing flood area with increasing catchment size with this one. I haven't had a chance to discuss that with the modelers yet, so I'm not quite sure what's going on there. But it's an interesting exercise in comparison. Okay, so conclusion so far. Thanks to the model developers for sharing their data and being so transparent, because without that, this wouldn't happen and we wouldn't learn from this process. As you've seen, the models are actually a complex chain of models with lots of different components, and some of those are shared. Interestingly, from this exercise, just putting this analysis together, we found some interesting anomalies by comparing the models, and that's led to improvements in the models themselves. So that feedback's already happened, and we're already looking at better models because of this exercise. There are still large differences between the models, and my personal research interest is in pinning down the process reasons for that, and perhaps the model structure reasons for that. So that's where we're going to go next. But we also need to be very clear on what scale we can use these models at, and what's their applicability to retain some sort of credibility in the models. The next steps, we need to do some more analysis, but by climate zones, starting to look at processes that might be involved. And in terms of validation data, we've got some microwave data from JRC. We're not quite sure how we're going to use that yet because it's not tied to particular return periods, but it might be useful for spatial patterns. And of course, we've got Dartmouth Flood Observatory are going to provide a MODIS-based flood map with some calculated return periods at different locations and different places. And of course, there's some well-studied places in Africa in terms of flood events that we can use those studies to look at this. Yeah, I've already mentioned that bit. So some final thoughts really quickly. Do we need a standard framework for the future, common formats, open access, to accelerate this process and to make it open? And for example, do we have create a standard flood validation database so that modelers can compare directly to a standard set of results and say, okay, not results, but observations, and it becomes a standard method then that they can compare to. Plenty of other models have been promised, and if you're a modeler out there or you have access to models, please, we're welcome to take any more. Any ideas and suggestions welcome as well. This is a collaborative approach. And visualization methods, I think, will be quite important in terms of sharing the detail of these comparisons. That's it. Thank you.
Thank you very much for the talk. Other questions? Yes, at the back.
So I think Castro and apologize that to me that there's no reality check in terms of actual flow data in this, but I'm not sure maybe I missed that. So I guess my question would be, if this was mostly virtual in this approach, wouldn't you be better off testing it in somewhere like the US and see how it does when you have real fluidity analysis and sort of real floodplain analysis, and then see how it does? It seems like there's no way to really validate this.
Well, yes, that would be very nice, but a lot of model developers don't want to share for the US because there's commercial concerns. So that would be nice, but not necessarily easy to do. Ultimately, it would be nice to scale this up and do it for the whole globe anyway. And I think we'll see how it goes the next meeting. But and also we do have validation data. As I said, we've got this Dartmouth Flood Observatory data. We've got GRC microwave data, and that's the next step. Now, the other thing we can compare to perhaps is the GRDC data for specific flow locations, but the modelers haven't provided that flow data yet. But that's equally possible. So I think it's quite easy to go to that level of validation without too much difficulty. Yeah.
Any further questions? Mark?
I just noticed that the forcing is different between the models.
Yes.
I think that may also be a big...
Oh, I think so, yes. I think that's probably one of the biggest. But we need to sort of narrow down what the various things are. So.
Okay, thank you very much, Mark, for the talk.